Okay, next subject we're going to talk about is Quaternions. Um, I'll tell kind of a funny story first. Quaternions are kind of interesting in that they're pretty like unintuitive, but at the same time very, very intuitive. Uh, Quaternion kind of represents an orientation in space, if that's the way you want to think about it. That's my recommendation as well. Kind of think about like I'm looking that way. That's the best way to think about it, in my opinion. However, they're really unintuitive in the way that they function. Like, here's a really good example of just how intuitive they are. So here's a visualization tool. You can like Google Quaternion visualization, and let's turn this on. And so you can see how this orientation is turning about. It kind of pops out of it kind of jumps across that x-axis. And what's really important is take a look at these values, w, x, y, and z, where the Euler angles here are clearly, there's like a pattern that makes kind of sense. Here, it's not necessarily the case. So like, for example, if I turned off this animation and I just started to change the y independent of these other values, you see how the other ones are weird, like kind of respond weirdly. Whereas here, it's more of a intuitive approach. It makes sense to everybody. But the values above, you can see how there's a sort of interplay where you're switching around. So it's not like one-to-one in the intuition of how rotations work, but Quaternions have a number of extremely valuable, aspects that are really, really great. Like for example, a rotation matrix is 4x4 matrix, right? Whereas Quaternion is just 4 values, so it's smaller. Rotation matrices also have if you're dealing with Euler angles, you have the problem of what's called gimbal lock, which we'll talk about in this lecture as well. And so taking the time to kind of get comfortable with Quaternions is really great. And so this lecture might be a little bit longer than it needs to be to just introduce you to the ideas. I really want to get as deep as I can. I'll tell a little bit of a story in that one day I had a friend of mine come to our office, and he walks by and he sees this textbook. And it was like a full textbook, and all it was just called Visualizing Quaternions. It's like a whole book. It's like 300, 400 pages. And he looked at me, he's like, do you need like a whole book to talk about Quaternions? And he kind of looked at me and he's like, yeah, you definitely need a whole book. Even though the math like is pretty easy to understand at first pass, their applications are pretty interesting. And we're actually, cool story about Quaternions. I think they were used in the Apollo computer to basically orient the Apollo spacecraft in space, which is really a big part of how they were able to be successful in those missions. And so, very cool stuff. So let's talk a little bit about gimbal lock. I think this is a really valuable little thing to kind of pay attention to.
In this tutorial, we'll look at Euler rotations and gimbal lock to see how strange motion can occur in between keyframes. In the last video, we saw that Euler rotations have a rotation order that can be changed with x, y, z values. We'll explore this further with a quick example of setting up the rotation order of an object to avoid gimbal problems. So how does Euler work? This gimbal machine shows us. Each part is linked to one another, so when the parts slide around, we can see how the rotations are passed on. By spinning each of the machine's 3 arms, we can rotate the jet into any angle. But notice when the jet points up, how 2 of the circular arms match up. This is exactly the same effect of gimbal lock, causing 2 circular arms to rotate on the same plane. Let's make this ourselves in a hierarchical system.
So that's kind of, I recommend watching the rest of the video, but the key is gimbal lock, right? If you've ever played a first-person shooter and you've looked up, and all of a sudden you kind of get stuck in that state, and you can't really go from up to here because you have to sort of know which way you're facing, and it's a mess. And so you get what's called gimbal look, where you look up and you can even get stuck in that state because the math has gone down to zero, and multiplying anything by zero is still zero, and you get stuck in that sort of position. And you can't kind of go backwards. So if you've ever played a space, like a flight game, like a fighter jet game, you can, right, if you pull up and you're looking straight up and then you want to pull up more, you can, but in a first-person shooter, you look up and you stop. And you can't look behind you. Not that you would want to, but in some cases, that's not necessarily what you want to have when you have an object that's spinning around. It's not a camera, it's just spinning, and you want it to spin and then not get stuck in a particular orientation. So let's think about a two-dimensional vector where you have the vector is like value of 1, 2, which is the rotation, a double rotation times the identity. Oop, there we go. Sorry, malfunction. And now let's think about a 0. Okay. Now let's talk a little bit about the quaternion. And let's put another vector there of 0, 1. So this is just a unit vector in the direction of the y-axis. If you add the 2, you get a position of 1, 3. So now let's talk a little bit about complex numbers. What happens if our value is actually going to be in the complex space instead? So you have a value of 1 and 3, but the 3 is actually a complex number. So I being the square root of -1. It's not a great explanation of this. Okay. What this is really trying to say is you can be in the real space, but if you think about this as a complex number, right? You've got a displacement of 1 and a displacement of 3 in the complex space. So that's technically you're still just on the x-axis. The value of h is a vector of the complex space, where y in this case is the complex plane. And if you think about this, you've got, right now, the real component is still just 1. And if you wanted to rotate about this complex space, you can do so in a way that's very similar to the unit circle with the xy plane. I'm not explaining this particularly well. If you guys want me to do another lecture specifically on the sort of complex math quaternion, I'd have to create some new material to do so. I don't feel like this is really representing it particularly well. The point that's trying to be made here is that a quaternion is made up of 4 values, A, B, C, and D, usually in the literature. And A is just a value, or sometimes referred to as W, X, Y, and Z. And so that is the real component of a quaternion. And then you've got components that are applied to the I, J, and K complex planes. So much like you have in the one-dimensional complex numbers have an x-axis and a y-axis, which is the complex plane. To do this in the third dimension, which we're all comfortable with one-dimensional complex numbers, three-dimensional complex numbers, you are also dealing with the j and k complex plane. So Hamilton, the mathematician Hamilton, came up with this. He was trying to figure out how do you apply complex number math. What is an algebra that works for complex numbers in the third dimension? And he realized that in this case, right, I squared is -1, j squared is -1, k squared is -1. But if you multiply all 3, somehow that's -1 too. So you kind of have to understand that quaternion mathematics is a different algebra in the way that 1 + 1 is 2. In this case, I times j times k is equal to -1. And if this is true, right, then you can have a set of algebras that provide you with these rotations, these arbitrary rotations in three-dimensional space. And by three-dimensional space, we're talking about the complex plane and doing complex manipulations of like a three-dimensional complex number. This is where my knowledge of mathematics kind of ends. I don't know if it generalizes to n dimensions, complex, whatever, I don't know. But I do know that it works quite well for 3D, and I'm assuming it works pretty well for 2D as well, given that you can do quaternions in a given fixed plane and so on. So I'm assuming that this can work in larger dimension spaces if you really want to kind of do that. With that bumbly explanation that I just gave, let's watch a video about quaternions that might be a little bit better than what I just did.
How do you rotate an object in 3 dimensions? So you take an object like that and rotate it. That would be something that's useful, you can imagine, in computer graphics. But how are you going to do this? Now, one of the neatest ways of doing this mathematically uses a new type of number beyond the regular numbers you know. So there's beyond the real numbers, as we call them. They're even beyond the complex.
Oops. Sorry, I'm not sure why that happened.
Numbers, if you've heard of complex numbers before, it's even beyond that. They're called Quaternions. They're fantastic. So imagine that I want to move along in 1 dimension. So you're living somewhere here. And if I said move +5. +5 means you move 5 units to the right along this line. So I'd end up over here. If I said instead move -3, you might understand that means move 3 units, but that time move 3 units to the left. So that's how you move in 1 dimension. That's fairly easy, isn't it? All right, let's talk about moving around in 2 dimensions. And let's say I want to end up at a point over here. What that might be, 3 units this way, let's call that a 3. And then I move 4 units up, like that. One way you could write that as a set of instructions is to write it as 3 + 4i. Some of you may know what's coming here. Some of you may have seen this I before. But for now, let's just say I means turn 90 degrees and go up and down. Right, for now, that's what it means. Right? So that's one way I could travel to that point. Or alternatively, I could look at it this way. I could travel 3 across and 4 up. Or I could rotate myself to this angle here and move along this diagonal line here. And that would be 3 + 4i as well. Right? You could use the same instructions to make that point. That's how you travel in 2 dimensions. I mean, if I want to then go further and travel maybe a bit further on, so let's say I wanted to go maybe 1 more across and then 2 up, like that. What I could do then, by adding a further 1 + 2i, I end up at this point, and I can say that this point is the combined result, which means I've actually travelled, what, 3 across and then a further 1, 4 across and 6 up. Or, if you like, it's the combined result of going from here up to here. So we can add these numbers together, and we should think of them as numbers. Right? You can add them together, and you can move around in 2 dimensions. So this time, let's rotate this line. Let's take my combined result here. What have I got? This is 4 + 6i. Let's rotate this 90 degrees. If I rotate it 90 degrees, I think it's going to end up something like that. And it will end up here. It will end up on a point here. So this is going to be a 90-degree rotation. This point is actually -6 + 4i. And that's where I end up if I rotate. These look similar to each other. Why do they look similar? How can I get from this number to this number? What I've done actually is I've multiplied. Instead of adding the numbers together, I've actually multiplied this time by the number, we call it a number, the number I. So there is a special rule with this. The special rule is I times itself, I times I, is equal to -1. Just to show you what I did, I took where I was, 4 + 6i, I multiplied it by I, and what did I get? I got 4i plus 6, well, let's call it I squared. Oh, what is that? That is 4i minus 6, yeah. Or in other words, where I ended up here, -6 + 4i. So multiplying by that number I means you rotate 90 degrees. If you do it twice, you get -1, which does make sense. So if you rotate 90 degrees and then rotate 90 degrees again, You're 108 degrees now, you're facing the opposite direction, so you're going negative direction, so it does make sense. And it turns out that if you multiply these numbers together, you get rotations. When you multiply the two numbers together, you add their angles together. So if I want to rotate 45 degrees, I'll get my triangle for 45 degrees. 1 over root 2 there, 1 over root 2 here. So that's nice, and that's a 1 now. That is a 45-degree angle. Written as a number, that is 1 over root 2 plus 1 over root 2, lots of I. There you go. So I've gone that distance across and then that distance up. If I multiply by that number, I would rotate by 45 degrees. So adding them together makes you travel around in 2 dimensions. Multiplying them together makes you rotate in 2 dimensions. Now, if you're ahead of me and if you've seen this sort of thing before, you may recognize these as complex numbers, which, by the way, is a terrible name, complex numbers, which makes them sound like difficult numbers, which I don't think is the intention. I think the idea is they are compound numbers. They are actually 2-dimensional numbers. That's a way of thinking of complex numbers. Real numbers are 1-dimensional numbers. Complex numbers are 2-dimensional numbers, and you can use them to travel in 2D and rotate in 2D. So the question is, how do we rotate in 3D? We must need 3-dimensional numbers, right? So we must have to introduce an I and a J as well. So we have 3-dimensional numbers, and that's what people thought. It turns out we don't need 3-dimensional numbers. We need 4-dimensional numbers. To rotate in 3 dimensions, bizarrely, you need a 4-dimensional number. Let me show you how this works. So that's right. So there was an Irish mathematician called William Hamilton, and he was thinking about this problem, and he couldn't solve it. He said, it doesn't work in 3 dimensions. I can't get it to work. And the story goes that he was having a walk with his wife along the canal in Dublin, and then suddenly inspiration struck, and he realised, I don't need 3 dimensions, I need 4-dimensional numbers. I need I, J and K. So flushed with this, he immediately walked over to a nearby bridge over the canal, and he carved in the rules that he needed to make this work. These are the rules that he carved into that bridge. I squared is equal to the j squared, which is equal to the k squared, which is equal to I times j times k, which is equal to -1. It's very similar to the complex number idea. Complex numbers, I squared equals -1. That's what we needed for that. It's very similar, but no, we need I, j and k. He carved this into the canal bridge, which unfortunately, graffiti, what a vandal. Unfortunately, it's not there anymore, but now there is a plaque celebrating the rules, or his discovery of quaternions. The rules are there, and every year mathematicians around Dublin have a pilgrimage to the spot where he had this idea for quaternions for the first time. So by multiplying these 4-dimensional numbers, you can now rotate, like the 2D version, you can rotate things in 3 dimensions, and this is how things are done using computer graphics. But not only that, it's how things are worked out for the rotation or the orientation of a space shuttle going up, or it's how they work out the orientation or the rotation of your smartphone. So let's say I want to rotate an object in 3 dimensions. What I do is I pick a line like this pen here. I stab the object with this pen, and then I can rotate around this pen here. So I might stab it this way, and then I can rotate the object like that, or I might stab this way, so it rotates the object this way, or else this way, and so we can rotate like that. So how do we write this? So I take a line like that, and then I want to rotate around that line. Let's do an angle of theta like that. Let's call it V. This line we're calling V. So it's a 3-dimensional thing. It has 3 coordinates. So let's call it V1 and V2 and V3. Let's take a point that's getting rotated around. So let's call that a P. and that's just x, y, and z for that point in 3 dimensions. This is how things work. But now we're going to rotate it using a quaternion. What does a quaternion look like? It looks like this. A quaternion, let's call it H, would be something like A plus BI plus CJ plus DK. And actually for this I do need another little thing, something called H star. And H star is A minus BI minus CJ minus DK. Right. If I want to rotate by an angle of theta, A, B and C are defined as A is going to be equal to cos of theta over 2. B is going to be written as V1, that's come from my vector here, that's my stabbing pen, sine of theta over 2. The C is V2, lots of sine theta over 2. And the D needs V3, lots of sine theta over 2. So it turns out we need 4 components for our number that we're going to use. We need 4 components to have the freedom to do the stabbing and then the rotating around that vector. And how do you work out the rotation? And then finally, if P, which is the point I'm rotating, you write P as a quaternion. Its coordinates are x, y, and z. It's actually x, lots of i, plus y, lots of j, plus z, lots of k. And finally, the rotation is h, p, h star. Right, that's the maths of it, right? That's the main maths. But we need 4 components to our number to have the freedom to be able to rotate around a vector and then move the angle around it. So the complex numbers contain the real numbers as well. And it turns out the quaternions contain the complex numbers, and in turn, they contain the real numbers. And when you don't need the j and the k, now you've got a complex number, and if you don't need the I, you've got a real number. So you might be thinking, what's next? Is there a next step up? And there is. The next step up is octonions.
All right, going into the weird math, we'll leave it there. If you want to keep watching, do recommend it. This is a great YouTube channel in general. But hopefully that gave you a bit of an understanding or a bit of a grasp in the math of the stuff. But you'll probably be happy to know that most of this stuff is usually done with an external library, and GLM does provide us with the capability to do quaternions without having to do the math at that level. One final thing is we'll talk a little bit about slurp, which is the effectively the ability to linearly interpolate rotations with quaternions. I think this is a really valuable watch. We'll just watch a little bit and see what's up.
So you've probably heard the term quaternion before. It's this thing that pops up all over the place in game development because it has this amazing property of being not only able to represent rotations in 3D space, but also being able to smoothly translate between them. This might not seem like a big deal, especially since the built-in lerp method for C-frames already handles the rotation translation, and to be honest, you're right, it's not a huge deal. You probably won't get a lot of quaternions on a platform like Roblox. However, if you choose to branch out, it's almost guaranteed you'll see quaternions again. So whether you're just curious like I was, or actually want to learn and apply this stuff, you're in the right place. Before we can get it...
Okay, maybe watch this on your own. None of this is more about... So, effectively, what quaternions are particularly good at is linearly interpolating rotations. You saw prior, in a previous one, I was saying you can't really take one rotation matrix and linearly interpolate it into another rotation matrix. This kind of makes sense, right? Like the values of sine and cosine, the trigonometric functions, are not linear. They don't go whoop. And so if you do, as we know now that the rotation matrices are made up of these trigonometric functions, you can understand that you can't go from one to the next and have a linear rotation. It's not going to just you're going to get these weird artifacts, and while your start and end positions may look the same, the stuff in between may look weird and not make sense. So quaternions are particularly good at creating these very gradual rotations that go from one place to another, because quaternions have a property that allow you to take 2 quaternions and to determine sort of what, and represent by way of another quaternion how to get from this orientation to the other orientation. And this is something that is really valuable about them, because then if you have that, you can, quantize that down into smaller steps and then linearly interpolate it on that rotation, versus the way you do a lerp over a traditional rotation matrix is you have a value for the theta and then linearly interpolate that value instead of doing it at the actual rotation matrix level or at the transformation. And so with quaternions, you can do this. Is it a really big deal? It's not a big deal, honestly. Like it used to be back when a lot of this stuff was extremely expensive computationally to do. Today you find it less so, but it's still really valuable, and you'll find it in most game engines. So GLM provides you with all the stuff you need to do quaternions. So hopefully at this point you're like, whew, I don't have to do that. I understand. I feel you. So the GLM library provides it with Quat, Quuat. That's giving you the identity quaternion, and or you can define it yourself with the W, X, Y, and Z values, or like I said, sometimes they're called A, B, and C, and D, but X, Y, and Z kind of represents the fact that that second portion is the vector about which you're rotating, if you want to visualize it in that way. You can also create a quaternion about a particular vector in this way, or you can do something a little bit more advanced, which is more controlled, where you can create a quaternion off of an axis. So you provide a rotation angle plus a rotation axis. In GLSL, this is on the shader side, you don't create quaternions. However, you would want to, by this point, the GLSL should not be ingesting quaternions. At this point, you should be receiving a transformation matrix of some kind, and you can do this when you're passing your rotation matrix and so on into your shader. So this is important because the quaternions do not contain translation, they don't contain scale, they're just an orientation. So very often what you'll have in an engine is you have an object with a quaternion-based orientation, and then when you're ready to render, you take your position, orientation, and scale, you collapse it down into one transformation matrix for the model that then gets pushed into the shader side. So how do you tell if two quaternions are the same? Well, their dot product will be 1, and this is one of the few places where quaternions do behave like traditional vectors. To take a dot product of two quaternions, you just do the component-wise multiplication. So A times A plus B times B plus C times C plus, and you just throw away the yeah. No, you don't. You don't throw away the complex. Cool. So, right. If you're doing this with GLM, if you're doing this mathematically, there will be rounding errors. Keep in mind, it's pretty difficult to know the two quaternions are exactly the same. The numbers may be similar in some cases. You can have two quaternions that represent the same orientation. They're not entirely unique. This sort of makes sense if you think about it, right? You can have two vectors that are different, that an appropriate rotation about the vector will get you to the same point. So keep that in mind. Like, quaternions get a little bit weird. This is a bit beyond my mathematical grasp of them even, but keep in mind when you do a dot product of two quaternions, you will likely have a little bit of error. So in general, when you're writing an engine and you're building this kind of stuff, you do want to maintain some kind of epsilon, some kind of upper or lower limit of error that will that you can then check against, and that will help you out in making sure that your calculations are within limit. This is in particular helpful with physics engines when small differences in truncation errors and floating point multiplications don't exactly hit the exact same thing every single time or on every computer. So yeah. What's nice about quaternions, and this is sort of gets back to what I was talking about with the interpolation. Um, Combining two quaternions is about as easy as you can get, which is just you multiply them together. Uh, Multiplication of a quaternion is not the same as a dot product. It's not the same as even a cross product, or it's different. It's its own thing. It involves the quaternion conjugate. But if you're using GLM, it's pretty easy. You just multiply them and it'll overload it for you automatically. You don't have to think about the math that's underpinning the combination of two quaternions. Although sometimes you'll find that just adding them together will work pretty well. But that's not something I recommend doing. So how do you interpolate between two quaternions? And we use this with the slurp, which is effectively means the spherical linear interpolation. That's sort of what I was talking about before. So this is going to show you a little bit about the slurp. Ooh. Okay, I'm not really sure what this is showing. This is not very descriptive. But what this is trying to show is that that blue dot in the middle, that's what you're going to get with a linear rotation. It's not going to really line up. You have the trigonometric functions are not linear. They have a curve to them. And so if you if you linearly interpolate a matrix, that you're going to get this weird looking thing, and it's not exactly what you want. It's going to go from one place to the next place, but really you might want to do this arc in between. A quaternion interpolation will give you that arc, and what you're doing is you're actually effectively splitting up that rotation into many, many small quaternion rotations. The way to do this, well, is not obvious. You don't want to incrementally rotate something, because what happens if you just take, okay, from here to here and then divide it by whatever 10 time steps, your end result's going to be kind of off. So what you want to do is writing a good spherical linear interpolation is non-trivial, and often you want to use external libraries to do that. But if you want to do it yourself, you just have to make sure that the start and end points are correct, or that you're using not necessarily an incremental or an accumulation approach, but rather a calculation of from here to here, from here to there, and calculating it at every time step, not just adding. Because often with linear interpolation for translation or an actually linear thing, you can take the line and chop it into 10 chunks and then add. But when you're doing the quaternion math can have error on most computers because of you've seen these values. These values are not usually happy numbers. And so often if you spherically interpolate a quaternion rotation at sufficient number of steps, your end result's going to be just that error will accumulate. So you don't want to do an accumulator like you'd be able to get away with if you're doing just a basic translation. Nope. So finally, the way you would do it is, like I was saying, use the slurp function from GLM. That's the better way to do it. But you don't want to do it. You want to use mix. And mix is just basically this the same idea, but it allows you to mix between two quaternions, which actually works particularly well. So yeah, that's about it. Quaternions are particularly valuable, powerful tools. They're used everywhere in from everything from just orienting an object in 3 dimensions. It's one of the best tools that you have. It's significantly faster. It's better, more accurate. It doesn't have issues. In fact, most engines underneath the covers while they give you X, Y, and Z angles to manipulate, because to a human being that makes intuitive sense, because you've seen Quaternions are not super intuitive. But underneath the XYZ, it immediately turns it into a Quaternion. That's a much easier way to work mathematically, because while we don't really, it's hard to explain them, it's hard to understand them, they, once you have them, they're very easy to manipulate and work with. And so that's about it. Yeah, cool. So that's it about Quaternions. If you're a bit confused about them, don't worry. Most people are. Most people that have worked in the industry for 20 years still don't really understand them, and that's normal. So just all you need to know is that we use them, and they're powerful, and at one point you're probably going to have to look up the equations online and encode them into your program. Great. Thanks for watching.